get going then. So again, today will be a little bit light and a little bit more like theoretical, but I think some of this is like worth at least having the words for, even though I'm not gonna like make you do a bunch of stuff with this. So I said overview of computer architecture for earth scientists, but then I didn't really bring it back until the last slide. So we can talk about that a little bit. But before we go into me just spewing words at you, I wanted to talk about like what is everyone's level of comfort with like computer hardware and like and computing in general as we go into this class. So I mean, I can give you like my little background and why I think this is worth doing. So my undergrad degree was in physics with a computational science like emphasis. And like one of the most memorable experiences that I had during my undergrad was my electronics class, where we literally built a computer. Like if you all know a breadboard, it's like just where you plug in circuits and stuff. And we built it like from scratch. It was like a month-long process. All it could do was add 4-bit numbers. Like it could add like numbers between 0 and 250. That's like all it could do, and then it would display on this little tiny thing. It took months of like time to do it. So and that sort of to me was really like informative of like, holy shit, this thing is magic. But then, as you like work with really large data sets or really large simulations, you start bumping up from it on the other side where you're like, like my program is like run Earth system model, but then it's like very slow or it crashes and you like, or, you run out of storage space and you go like, oh, what's going on? And try to debug it from, top down versus bottom up. I mean, I think having a little bit of a holistic idea of like the whole spectrum of computing is worth having in your head, just so when you're thinking about especially for any of you that want to go out and do field work and do like embedded systems and sensor design, like this stuff will come in. Or if you're a person who's trying to do really large simulations and want to like understand some of the bottlenecks in these very large computing systems, I think that's sort of where I come at it from, seeing both ends of that. So with that, what sorts of hardware are you all familiar with? Everyone has worked on a laptop or like a PC before, but does anyone else have other experience working on other systems? Let's go around it. Yeah.
For me, also my background is civil engineering, so I had no experience at connecting breadboards.
Okay, cool.
So personally, I do not have that much experience of setting up a PC, but I have opened up the CPU and looked into it, but do not know very details of that.
Also, my background is civil engineering. We never had course something like that that's been into something from scratch for the computer, and we used to design a building with the already developed model. But when I was younger, because I used to play video games, so always every year I need to update my CPU and everything. So I used to add more CPU every time, or RAM, something like that. But except that, no.
Oh yeah, and I don't necessarily mean specifically like working with hardware, because I'm saying I know you work on my server.
Yeah, so with servers, yeah. So I have a lot of experiences about the servers. So during my master, I used to run the model, the hydrological modeling that I couldn't run it for the Windows, and I had to run it on the Linux for the first time in my life. So that was a good experience to see how I should set up these things on the Linux, especially Ubuntu. I mean, I used Ubuntu at that time, and then during my PhD, so because I need to use GPU and CPU and parallel coding, so I couldn't use my laptop because it doesn't work sometimes or it's very slow. So because of that, I had to use GPU and CPU for that. So
And Anik, I feel like you probably running NoMP stuff. Are you working on like HPC or
Yeah.
supercomputing systems?
Yeah.
So
For my PhD, I have started working with a server for the NoIMP. But for my current responsibility, Goyu has asked me to convert his Fortran code into Python. So I haven't still run that NoIMP into the HPC server.
okay, so you have both sort of working on those systems and also translation. Yeah.
not my experience, but the first time that I started to use Ubuntu, I scared a lot because there is just terminal and you should just
Mhm.
write everything, move everything, copy, run, just be writing something. And just so scary for me, and I didn't know what should I do at that time. Also, there wasn't any AI. You just search it on the Google Chrome or somewhere like that to search and figure out what's going on. But I don't know you guys working on that or not. But after 2 or 3 months, you feel much more better, and you don't like to back to the Windows or other things. And whenever you want to do something else on your laptop, you like to use terminal for that,
Yeah.
because it's faster, it's easier. And also one experience that I had, so I started to use first CPU, and then I started to use GPU, and I could see how GPU is much more stronger. And it was really amazing for me to see how these things work and how much GPU is more powerful compared to CPU.
We won't talk about that today, but I do want to, because I think that's more important for the whole class to see eventually. We'll talk about.
In terms of hardware, so I went to community college, and so I didn't have like the normal like first 2 years of hydrology. I just did engineering for the first 2 years, and so I took a circuits class with a lab, and I had this similar experience of you can build like a huge thing on a breadboard with all these moving parts, and all it will do is make a car go around in a circle. Or
But that when you finally get it to work, it's like
oh my gosh,
yeah, right.
Yeah, it takes forever. So I thought that was kind of cool. And then in terms of computing, I learned how to use my terminal back actually in community college. I came here for a summer research internship, and I was working in geoscience, and I was working in geophysics. And then the guy who I was working with just taught me how to use it. He sat with me for like 6 hours every day for like
Wow,
that's about a month. I know, and he's a really good professor. He's from Harvard. Yeah, he's so super patient. I talk to him still today. And so he taught me how to use the terminal, how to go into my files and everything. Doing that, I've become lazy. I just click on the whole files folder now. But I do use PowerShell on my computer, and then I'm just familiar with the CPU system. I personally haven't used the GPU. My like office mate over the summer at the national lab was a cybersecurity guy.
Oh,
cool. And so he would like tell me all about like CPU versus GPU and like all that type of stuff and how. Yeah, so I just picked this brain a lot on lunch and stuff.
So I have simultaneously a very broad understanding and also very niche understanding depending on applications. So in terms of hardware, I have experience with designing PCs and for like consumer side of things, and then having them like pre-built for me. And I have looked and dabbled a little bit into building my own PC, but nothing really. I wouldn't say I'm the person you should come to with if you have questions. Don't come to me. I'm not that. I know only what I can cursorily get, and I've only started on that journey to try and build my own. And in terms of like software, I have experience with Terminal. Most of the stuff that I do is in Python. As much as I like Terminal, and it's very useful, I abhor having to use Terminal. If I can avoid it, I will. But I've worked with using there's a supercomputer over in Stewart Observatory called Nimoy, and we did a back in my undergrad, there is one class that everyone has to take where all you're doing is work in Nimoy. And at the time that I was doing it, they didn't have like some safeguards in place, and somebody decided to delete the entire server, and they got in serious trouble. So now it's admin locked. So no one can join Nimoy unless you know the secret password and know who to talk to get it. So I had experience with using Nimoy and having to do a lot of stuff with just terminal and like tar-based files and dealing with basically file architecture issues. And in terms of like building circuits and things, I have never used a breadboard. I've always wanted to use a breadboard, but I only have basic circuitry understanding on that side of things that I got from my physics minor back as an undergrad. And it's been probably 3 years since I did anything in terminal, at least extensively. So I would probably need at least a few hours to look at the terminal and go, what am I supposed to do here again? How do make work?
CDLS, CDLS.
Yes. 100%.
And like that was all in like Linux and stuff.
Yep.
So applying that to Windows is, there's some things that I am like, on my own Windows PC, I'm like, thank God terminal is still used because I can do this so much faster in this regard. But that's a very narrow like file architecture type modifications and things in that nature. And I do have some small experience using both serial bus and COM port / networking modifications, but that was probably 3 weeks of like classwork 2 years ago. So cool, again, broad and simultaneously very shallow.
I was wondering, at the end of your last class that I took, the 401, 501, we used terminal, I remember at the end, just like this, very small, but I just remembered that, right, as he was like 2 to 3 weeks. I was like, oh.
It's like, if you showed me it, I could probably tell you what it is, but I could not explain to you how is it working on the back end to make it actually function.
Well, we'll talk a little bit about that today. And actually, I should have included a little bit of language on that. Either way, we're good. So it sounds like everyone has at least a little bit of experience with at least like a terminal experience and possibly working on systems that aren't just your laptops. So that's great. That's awesome. I just wanted to kind of level set and see where things might be useful. We could do a bit more deep dive into some terminal stuff, but that's, again, it's pretty dry. It's pretty whatever, but it's also like, what if it can speed up your research so much. So we can talk about that. I have some excellent recommendations, especially for like Linux-based systems and stuff that I'll toss some resources up at some point. But okay, I'm just gonna get into it then. So all computers use, at this point, hand waving. This system called the von Neumann architecture, which was sort of come up with primarily by this guy, John von Neumann, in, I believe it was roughly the 40s. He was an applied mathematician who worked on like a crazy amount of stuff. Super weird guy. Again, I'll try and toss some little history pieces.
Numerical methods.
Yep.
Yeah, von Neumann
Huge.
stability. Yeah,
Huge
it's like
in numerical methods.
Von Neumann probes.
He also invented game theory. He also thought we should preemptively carpet bomb nukes on the Russians. So, the good comes with the bad. Again, brilliant man, fixated on ideas, whatever. But he and others, but it's named after him. So, you have to throw a picture up or whatever. Sort of came up with this sort of consolidation around how you can design like modular computers, because before that, see, now I'm talking about it, I'm getting these ideas. So back in the day, computers, when they were like designed, they didn't have this general purpose idea. You would build the computer to solve your problem. So you would encode all of your data in the hardware, and then you would run it. And so this is sort of like the innovation of this von Neumann architecture is the idea of separating these three components: the input output, the processing unit, and the memory. So CPU is generally, I'm calling it processing unit, as we've already thrown around GPU or other types of processing units. But back in the day, this was the only one that they sort of had. And so this idea of separating these three components is what we're left with in the world. And all computers that practically you're going to use this. There are other architectures out there. Things like quantum computing are still in their early days, where they still often are circuits that are only designed to solve one problem rather than a specific one. So there's some pushing on general quantum computing, but it's still probably decades out. Same with things like neuromorphic computing, which are designed ideally to mimic like heterogeneous circuits inspired by biology. There's also like some cool stuff that's happening with photonic computing, using light directly rather than electrical signals. But you probably won't use those anytime soon, so we're not going to focus on them. And so again, it's a very simple diagram, right? But I think it's worth thinking about for a second, because again, as circuits previously were designed for a specific purpose, this really was like a light bulb moment of like, what if we could just store data and use it later? And that's this input output. So, right, like all of your models or data analysis, you have some input data, and then you probably do some analysis, you make a figure, and you output it. So this is sort of the core, these are the parts that we really care about, and all of this stuff, we just want to do a job for us, right? And so how this works is there's this separation between the memory units, and we're going to dive into the memory stuff in a little bit more today, and then the processing units, which we'll talk a little bit about today, but then more next week in more practical terms. And so I'm sure many of you know your computer has a storage disk, that's the IO. It has the memory unit, which is your RAM or your system memory, and that's this guy. And then it has this control unit, which here has two sorts of things. Originally, computers were designed to do like not very much, and now there are many different types of processing units. So the control unit is like the orchestration thing. It decides where things need to go. And then originally what they had was this, what's called the ALU, the arithmetic logic unit, and all that could do was arithmetic. Everything on computers in these days, and even still today for the most part, it says arithmetic, but we can do like floating point calculations, we can do string operations. Everything in computers is eventually translated to this, and the reason for that will come up in a second. Okay. So going from this like high level description, right? Like that's a very like, it's got a couple components. How do you go from that to the actual like circuit? And that's all done with basically binary logic and these sort of 5 fundamental operations of logic. So if you've ever taken like a symbolic logic course, these are your and or not. And then there's not and not or, which are combinations of these, but there's more efficient ways to design them. As 2 fun facts here. First of all, NAND is actually the only circuit you really need. In practice, you can make faster circuits by combining these, but NAND is like logically complete. You can make any circuit out of only NANDs. Just a fun fact. And the other thing that you might be wondering about is these are all implemented with transistors, which, modulated by voltage, say either it's on or off, right? Seems reasonable enough. And there's some noise in that, right? Like the voltage is a continuous value. So at some point, there's just a threshold that's set, right? And then it's either on or off. The other fun fact is, technically speaking, ternary or 3 logic, 0, 1, 2, is actually slightly more efficient than binary. But because of hardware complexity, we don't actually use it. And it's just because it turns out the, E, like 2.7, whatever, that's like the absolute best data compression you can use. And 3 is closer to 2.7 than 2, and that's the reason why ternary is, in terms of integer value logic, the most efficient. Okay, so from these building blocks, you can start to design your computer. And this is a slightly more complete picture of what a modern computer architecture will be. So I'll talk about input output, but what I really wanted to specify here is the sort of way that data flows and the direction of flow. So there's 2 types of arrows in this diagram. There's the command and control signals, which are in black, and then there's the data instructions. And realistically, everything flows from either a input output device to or a memory, or like a larger memory device, into the system and then back out. So this is like, again, everything we care about in computing is being able to do something and produce new data or something like that. The other thing in this figure that you'll see is so we go from input device, it goes into main memory. This is your system RAM. And then almost assuredly, it will go into this route. Otherwise, if you go like input device, memory, output device, that would be like just copying a file, right? Like all you're doing is throughputting it. But almost entirely what you're going to do is go in here. And this register thing is the important, I guess, clarification. So these systems have very small internal memories that can rapidly do this little cycle so that you can do compute faster. And so the idea here that's really important is there are levels of this memory hierarchy that that can be used for different purposes. So if you go in here through this and back out this way, that would be like a very small operation that you'd want to do, maybe just calculating a log or something. But if you have something that's a little bit more complicated, like some recursive element, like if you're calculating a Taylor series, what might happen is you end up going in through here and then back through this loop a bunch of times, which is much faster, and then finally back out and right to disk. Okay, so I think I just talked mostly about this. So then, yeah, so I guess I already explained why there are multiple memory types, but also like thinking about what constitutes input output is worth thinking about. And that's like anytime you save something to a disk, that's going to be an output value. And anything time you try to read new data that's not stored in memory, that's going to be an input value. Does that kind of make sense?
Sorry, can you say again like how we work with the secondary memory? I mean, what's the role of that?
Secondary memory might be something something like GPU, VRAM. And then that actually technically sort of has its own flip side copy up here because you're probably going to do something else with it. There are also other types of memory that aren't, it's not used a super huge amount. There's temporary file systems on computers that they look like your regular file system, but they're actually stored in a secondary memory storage, so for faster access. That you don't have, we won't talk really about it, but it's good enough.
Wait, I have a quick question. What did you say before about the input devices?
Yeah, input device would be anytime you're reading from a disk, a USB drive, your local hard drive. That's going to be an input device.
Okay, and then, so it's like an actual like physical thing.
Yeah.
And so if I go download data online, that's not an input device.
It is.
It is.
Yeah.
Okay.
But then we save it and you use it later.
So then that's just like input device, main memory, output device.
Yeah.
Okay.
Yeah.
Gotcha.
So if you're downloading from the internet, there's a computer somewhere. You're reading that data into your main memory of your computer that you're downloading it to, and then you're outputting it on the local hard drive.
Okay. So then if let's just say I'm running a numerical scheme on my computer, and I have to download data to do so. So I download data, and that would just go one pass, input device, main memory, output device, and then I run a numerical model. It will go input device, main memory, and then down loop through main
Do some
the CPU,
calculations.
and then go up again, and then output device.
Yep.
Okay, cool.
And similarly, if you are like uploading data to, a website or something, it's going to go the opposite way. Instead of downloading, uploading, it's, they're the opposite. So it goes from your computer, main memory, and then out to the network. And we're not going to talk like deeply about networking. I'm going to hand wave that whole thing and just say, it goes through a series of tubes.
And just a clarification.
Yeah.
And secondary memory in this case could be like any other memory type that is not being directly interacted with by the CPU during this loop process for an input.
Well,
So
you
you're
can
doing,
see
like,
there
parallel
is like a path. The secondary memory is sort of a catch-all for if you have other things that actually maybe that's worth a step back. Memory generally refers to systems where it's called volatile, which means if you take the power off of it, you will lose the storage. Whereas the input and output devices typically mean non-volatile. So like you could take the hard drive out of your computer, wave it around, if there's no power on it, put it back in and you don't lose anything. Whereas memory generally means if you take the power off of it, you lose all of the knowledge of what it meant.
Okay, so this is making more sense why you have when you buy a computer, you have like two memories. Okay.
Yeah, and so RAM is main memory, where like if you shut your computer down, it won't necessarily remember exactly what you're doing. They've done a lot of things to make that, more transparent these days, but for the most part, if you rip the battery out of your computer, it won't be able to restore the programs, right? Because that was volatile memory.
Yeah. And so when you pass it, let's just say you're doing another calculation, you go input device, main memory, goes down, and so you have like your coding language, right? In your so your coding language would be like an executable, right? And so that would be.
We've got slides.
Oh, okay, cool. All right.
Okay, so we're just going to start with this memory. So this sort of shows it's called the memory hierarchy, and with all of this, it's trade-offs between speed and storage size, speed of access and storage size, also cost to a certain extent or to a large extent. So the things, and we'll dive a little bit more. I'll give you some numbers in the next slide. But these processor registers are usually, like 100 kilobytes. They can store a few numbers, but that's about it. And so that's basically here. That's like super fast and very expensive small capacity. And then the cache, so there's usually 4 levels of technically speaking system memory on your computers. There's the RAM, which is the only one that you have actual control of. And then your CPU has these things called caches, where they store intermediate calculations. So if I go back here, where there's this loop here, that's where the cache comes into play. So registers and caches are sort of interchangeable to a certain extent. They could be considered secondary memory, but they're a bit larger. So if you're running a simulation in iterative numerical method, it's going to store as much of that internal calculation on the CPU cache as possible. And those typically are on the order of a few hundred megabytes. They're getting a bit bigger now, and there are different levels, but it's a little bit irrelevant to distinguish between them because you can't control them technically, unless you do very low level programming. And then we have like your storage, your hard drive, and that's, you know, up to 100 terabytes if you get like a really big beefy thing. But you know, most of our laptops are about a terabyte. So, and the other thing that I think is, so we've gone, again, power on, there's a little bit of volatility that you can keep within here, but then this is kind of where when you start to turn off power, you lose the data. And then this puts us at hard drives, which are just your standard storage. And then there's this very last piece, which I feel like most people don't see very much, but it's actually still really relevant, technically speaking. And it's this tape backup. So hard drives themselves are still somewhat volatile. And, you know, if you have like an old style hard drive and you shake it around a bunch, you can lose data. If you have newer style hard drives and it gets exposed to like radiation or something, you can lose data. There is like actually very real like computer engineering. Like we do get cosmic rays that do actually fuck with hard drives a little, like even the modern ones, which are more stable. And so tape backups are even more stable than that. They're written out to like magnetic tapes and archived, and they're very slow, but very hard to mess up unless someone goes in and like crinkles it up and cuts it and stuff. In Earth systems data, actually a ton of it is archived on tape backup stuff. So for instance, a lot of big remote sensing archive data sets, like Landsat or big climate model intercomparisons like the CMIP stuff, they are all archived on tape backup in addition to, you know, being provided via faster methods. That way, when there is data corruption, they can restore it. And one thing that it's kind of cool, for instance, the at the National Center for Atmospheric Research, NCAR, they have like a big tape archive backup thing. And if you try and go, I bet if you tried to go back and get like, we're on CMIP 6 right now, if you went back and tried to get CMIP 4 to access it, it's actually going to go out, like request a system. And there's like, you know, a big like machine arm that's going to go find the tape archive, bring it in, read it in, and then finally provide it back to you. So this is still like actually very relevant, and something that I think a lot of people aren't super aware of. Same with like deep backup archives, which tend to be very cheap on systems like Amazon Web Services or Google Cloud. You can get tape backups if you want to store data that you're like, we probably won't need this for years, but we never know. And so for big simulation archives, that's often where it would go.
We don't have the tape on our computers.
No.
We just have the hard drive.
Yep.
Very cool.
Yeah, the tape systems require like infrastructure because they are still like, you know, they're like big physical devices and require like a machine to like take it out of storage and physically relocate it to be read in because it's so slow.
Is that where you see like the old computers, you see the big wheels and you see the tape and they're, okay.
Oddly enough, there's a telescope on Kitt Peak that still uses magnetic feed tape
Yep.
as its main computing source. And it still works.
That's the thing. Yeah, I mean, that's the thing. Very, it doesn't have it on here. It's very reliable. Like, it's really hard to mess up the data on those. So I think it's worth, just talking about it. It's kind of fun. So just a more detailed description of this, just so that you have like it in your head. And I hope that these analogies kind of work for you. The registers are like immediate knowledge. You have them on hand. Then this cache stuff is sort of still technically around this processing unit stuff. It's very, very fast. It's still on the order of, tens of nanoseconds to get a small chunk of data, but it has, small storage. Then you go out again, your system memory, but, we're looking at an order of magnitude difference between these two. And as we go out here to your storage device, it's like 2 orders of magnitude. And then as you go out to your disk, it's, another 2 orders of magnitude. So you can see like, we're going from fractions of a nanosecond to tens of milliseconds. And then if you go out and are like downloading data, right? Like, again, remember the nanosecond is about that much speed of light. You have to like physically like, make a connection, go somewhere, make that connection and then ping back. So that's, for those of you who have been gamers, like if you have a bad ping or whatever, that's the round trip latency of a signal of like sending, some message from my computer over the network to another computer back. And so that's much, much slower.
Latency.
Exactly. So, and you can kind of think about it versus like, having like knowledge that like you're just like looking at it or going out to your desk or like, getting up or having to walk somewhere, order something. And this one is like, oh, I've got to like plan a trip now. So that's, I think it's worth like seeing the orders of magnitude because it really does in some ways affect what we do. Okay, so just we're gonna switch focus real quick. And now we're talking about how do you get from a thing that just does transistor signals, right? Ones and zeros to like what we do, which is mostly Python, maybe Fortran or whatever. And so the hardware is constructed. It's not like totally agnostic. They design circuits designed around this idea of an instruction set architecture. And this is a very low level language that's the boundary between software and the circuits themselves. And these are like predefined, they engineer them to do that and define these specific operations. So if I want to load a piece of data from memory or store it to a register or try to add it with the arithmetic unit, that's what it does. And all code eventually ends up being translated to this layer. And so this is a comparison between Python and this is x86, which is like your Intel AMD computer. This is the instruction set language, where if you wanted to print hello world, you can, it does have some capacity for higher level things, like it knows what a string is, but you have to like really define it. And like, you have to know this 0xa is the actual memory location where it's going to go. So it's like a specific place on the hardware. And so then you have to like move the data around, do a bunch of stuff here, and then tell the computer, which is, this is a higher level software thing, to actually like do this. And that's how this whole chunk of code is the same as what Python would produce here for print hello world. So there is a lot of complexity in these languages, and doing anything like this is like about the closest. This is the only thing I could fit on the slide. Like if you have to like do a for loop or something.
I'm so glad we have software engineers. I feel so thankful.
And the main point that's important here, and how am I doing on time? Okay, we've got a couple minutes. The main point that's important here is there are still different instruction set architectures. So if you compile a program on your Linux server and try and run it on your MacBook, it's not going to work, right? Because it's when you compile code, it will be translated to this. Now, the nice thing about Python is it's interpreted, so it does that translation dynamically, but that means it's much slower because it has to figure it out every time you run the code. What's the mapping between this and this? Versus if you compile like a Fortran code, it does this once, and then you can run it anytime, and it's perfectly translated for the computer, right? Yeah. Okay, so yeah, this is sort of the trade-off, and I'm sorry, this was the best, I thought, figure I could find. There are other ones out there. I'm gonna make my own now at some point after this, but there's this trade-off between expressiveness, ease of implementation, and performance. That often is the case. So these lower level languages, you know, if you have like, I need to solve this problem as fast as possible, you want to design a circuit that does it. If you're okay with, you know, mostly what we've got, you could go into those assembly languages, but most of us don't really need to do that. And so we use higher level languages, which would be like Fortran, C, Go, Rust, whatever. And then there are these other languages which technically don't compile down to the machine code, but have some intermediate layer, and that's Python, Java, JavaScript, etc., where they have some mechanism of mapping between their own language and the machine language sort of dynamically. And they tend to be slower. And then there are things like on top of that, like, I don't know if any of you have ever played with Scratch. It's like you can drag and drop little blocks. It's quite fun. It's what MIT uses to teach intro computer programming and stuff. And like you can teach it to like a 10-year-old easily.
And by level of abstraction, we mean ease of human understanding in this case. So like it's easier to understand things like Scratch or Python than it would be to have to engineer a specific hardware solution for a specific problem.
Yep. Okay. Yeah, generally speaking. I mean, level of abstraction is an abstract term in itself, right?
Yeah.
And so the high level language still goes down and just does that pass once.
Every time you run the code, it does that pass.
And then so Python, it would have to, as you're running the code, it would iterate through.
So the Python interpreter, if you run a script or whatever, it basically runs every single piece of code it looks at, or like scans it first, and then does some like, okay, these are the pieces I can throw away because maybe I don't use this or that function. And then it does the translation to the assembly language.
Gotcha.
But every time you run it, it does that. Which is why if you run, I mean, there are caveats in all this, but for the most part, if you run a Python script twice, it's going to take just as long both times. Versus with like Fortran or C, you have the compilation step, which takes some time. And for like a big climate model or something, it can take like a while to compile the code. Like NoMP takes, you know, not an insignificant amount of time compared to like running it for one time step. But then it's ready to go, right?
And so would Fortran be a high level language?
Yeah. Yeah. So high level language really means anything that's like written with text. Sort of technically assembly language is written as text, but I mean, I challenge anyone to know what is MAVRAX or, you know, like those, it's very hard to, because it's calling specific registers.
Complex text, but Python is easy to read.
Yes.
Yeah.
Yep.
Very easy to read.
Okay, so all of this, you know, we've got a shared computer architecture, but there is a lot of heterogeneity, right? Like we've got embedded systems where if you're going to put something out in the field, it probably has a computer that is not so different than your laptop or even a supercomputer, but it's much smaller, hopefully more resilient. Same thing with like, you know, smart fridges and stuff. Computers are like in cars, are embedded systems, and are actually quite, you know, surprisingly beefy at this point. But you know, thinking through like where do I run my code? Is it an embedded system where I really need to focus on like getting measurements from a sensor, or am I doing some small job on my laptop or a medium job on like a big workstation where you might have, you know, like a couple 100 GB of system memory? And then the last jump, so like these are basically the same, but the last jump is to supercomputers where you have multiple nodes, and essentially all a supercomputer is, and I'm, you know, hand waving here, but if you stacked up 100 MacBooks and had some way to very quickly communicate data between them, that's what a supercomputer is. It's just a rack of regular computers supplemented by a very high speed data interconnect between them. So really, if you understand this guy, that's all there is to computing anymore for the most part.
So if you have like a supercomputer, do they all do not share the same processing unit? Do they all have different processing units?
They do, yes.
Okay.
Just like if we were to stack up, you know,
Okay.
laptops, they have different processing units, but they can share data quickly between them, and they have software that essentially makes it easier for them to communicate that data between them. But ultimately, if you're going from one, you know, you would have a stack of these, and if you're going from one computer to another, it would basically, like if another chunk of your supercomputer needs some data, it has to go out here and then output and then transfer over the network to that other piece.
Gotcha.
Yeah, when you run these big, really big numerical simulations, that's what's going on.
So it's like another computer's input is the previous's output. So, okay.
And so this is where we get the idea of like parallel processing, where two computers are working two similar problems simultaneously, and then they're pulling together that information using like a third computer in that regard.
So there are multiple ways that you can do parallel processing at this point, and we will talk a bit more about that next week, because it's, again, there are multiple things. So there's like most laptops, even phones, have somewhere between 2 to 8 CPUs at this point, sometimes a bit more, but usually not more than 20. And so they share the same system memory rather than going out to a network. Supercomputers have specialized networks designed for them. And then there are also like optimizations where you can share the same memory and don't need to do stuff. And I'll talk a little bit about that and a problem with Python around it at some point. So, okay, the last thing I wanted to talk about. So all of this is great, and I think it's worth having an idea of it. But fundamentally, and this is why I talk about memory more, CPU speeds have gotten like insane. So for the most part, you know, computing focus has been, or like development has been focused on, can we speed up the CPU? But memory has not kept up with that pace. And so there's two problems with that. There's latency and then there's bandwidth, and they're both related to how fast you can move data. So the latency is how long does it take for me to like communicate that I'm going to do something with data. Once you get that connection, the next question is like, how fast can I move the data? So they're sort of separate things. It's sort of the same idea for those of you who are familiar, sort of between velocity and celerity, for instance. So there's two questions. How long does it take for me to connect? And then once I'm connected, how much can I move? And a lot of earth science sort of problems end up being memory bound, where for the most part, you end up waiting for your computer to read and write memory or transfer data over the network. And this is where we'll go next week and be talking about not just parallel processing, but also looking at like, how do you optimize your data for read and write? And we'll look at like some really big data sets to talk about things like how do you chunk your data up and modern approaches to storing these large data sets, which is super important for designing machine learning algorithms. I say this all the time, but like, my God, I spend all of my life writing data loaders and I write a model and it takes me 1/10 of the time compared to writing the data processing stuff. Like the like fun part takes very little time. The crappy part takes forever. And yeah. So yeah, that's all I have for you.
That was awesome.